Good afternoon. Today we'll be covering section 5.4 from Precalculus Enhanced with Graphing Utilities by Sullivan and Sullivan. I am Professor Shannon Gracie, and here we go. We'll be learning a whole bunch of stuff about logarithmic functions, and you can read the goals here. Let's go ahead and start by warming it up. So pause the movie and warm up, or you can just follow along with me if you'd like. Let's go for it. So I noticed that both of these, you could either look at them as 2 raised to powers or 4 raised to powers, so them being the bases. So let's take a look. So 1/64 is the same as 4 to the negative 3. And that's being raised to the 2x. And on the right side, 16 is 4 squared, and that's being raised to quantity, x squared minus 5. So when we raise a power to a power, we are multiplying. So we'll get 4 to the negative 6x is equal to 4 to the 2 times quantity x squared minus 5. So now we're going to go ahead and equate the powers since we got the bases to be the same. So since we have the same base, we can equate those exponents. So here we go. We'll have negative 6x is equal to 2 times x squared minus 5. If I divide out a 2 on both sides, I'll have negative 3x is equal to x squared minus 5. Getting 0 on one side, we'll have x squared plus 3x minus 5 on the other side. That one is not factorable, so x, I'll just go ahead and use the quadratic formula. So x will be negative 3 plus or minus 3 squared minus 4 times 1 times negative 5 all over 2 times 1. So x will be negative 3 plus or minus 3 squared is 9, and then 4 times 1 times 5 is 20. Minus a minus is plus, so we'll get root 29 all over 2. So those are our solutions. Negative 3 minus root 29 over 2, and negative 3 plus root 29 over 2. How'd you do? Awesome. All right. So now, second warm-up will be kind of a building activity to our lecture. So we graphed a couple times, I think we've graphed f at x is equal to 2 to the x. So if you recall, I'm just doing the ordered pairs now. I'll do the first one for you. If I do f at negative 1, that's equal to 2 to the negative 1, which is equal to 1/2. So on the graph of your function f, you will have the ordered pair negative 1, 1/2. So what happens for the inverse function? Good, they're going to flip, right? They're going to reverse positions. So we'll have the ordered pair 1/2, negative 1 on our inverse graph. And then continuing like that, if we plug in 0 to the original function, we'll have an output of 1. And on our inverse function, we'll just get, good, 1, 0. And then if we plug in 1, 2 to the 1 is 2. And on our inverse function, which we don't know what it is yet, we'll get 2, 1. And then if we go with plug in 2, 2 squared is 4. Our inverse function will be 4, 2. And lastly, if we do 3, 2 cubed is 8. And our inverse function will have the ordered pair 8, 3. So if we set our scale at plus or minus 10 on both axes. We'll just call them x and y since we're doing two graphs. So I'll do the blue first. I'll graph f in blue, and then I'll graph f inverse in green. So negative 1, 1/2 is here, 0, 1, 1, 2, and then 2, 4, and then up here at 3, 8. And so remember you have a horizontal asymptote at the x-axis, and then it increases without bound. Okay, so recall that we're going to have our inverse functions reflect across the line y equals x. So we had gotten, actual ordered pairs here, but you could have done this just by doing that line y equals x. So this here was our function f. Let's graph f inverse. So we'll have 1/2 negative 1, 1, 0, 2, 1, 4, 2, and then 8, 3. So instead of a horizontal asymptote, this guy is going to have a vertical asymptote at the y-axis, do you see? And then it's going to look something like that. Pretty groovy, huh? So this is our f inverse. Okay, so moving right along. A logarithmic function to the base a, where a is positive and a is not equal to 1, is denoted by y equals log base a at x. You can read that as y is the logarithm to the base a of x. And is defined by this statement. So y equals log base a at x if and only if a to the y is equal to x. So, okay, this is going to seem a little silly, but in my face-to-face classes, I make them do this. The main thing to remember is that a logarithm is an exponent. So what I want you to do is chant with me 5 times. Ready? 1. A logarithm is an exponent. 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 So if you have a log expression isolated on one side and a constant on the other, then you're switching it back and forth in these formats, that can be helpful, remembering that a logarithm is an exponent. Okay, so the domain of the logarithmic function y equals log base a at x is, whoops, I'll just do it regular here, x greater than 0. And in interval notation, you do 0 to infinity with parentheses around both. Interesting facts. Okay, so the domain of the logarithmic function is the range of the corresponding exponential function. And the range of the logarithmic function equals the domain of the exponential function. So just to remind you guys here, the domain of the logarithmic function went from 0 to infinity, non-inclusive. And the range of the logarithmic function, which is what we graphed in our warm-up, was all real numbers. Okay, properties. So basically here, the defining equation for y equals log base a at x is a to the y is equal to x if you switch it into exponential form. And the domain for the logarithmic function is 0 to infinity, non-inclusive. And the range is all real numbers, so minus infinity to infinity. So let's get a little bit of practice, just changing each of these exponential statements to a statement involving a logarithm. So remember, a logarithm is an exponent. So your base gets little. So first you have to write log. The base is what? Good. The base is 4, right? A logarithm is an exponent, so we can just say equals 2. And what's left? You got it, 16. So I used to just remember where the base went and what was after the equal sign, right? So where the base went and where the exponent went, and what was left went inside the log. Okay, so you try B and C and see how you do. Okay, so let's see how it went. Again, you have to write a log, right? The base is E. A logarithm is an exponent, so 2.2 is the exponent, and what's left? Perfect, M. And then what about this guy? Actually, you could write, if you write IFF, that means if and only if. So IFF is if and only if. I would have done a double arrow, but I did them below. So another way to do it would be like this. So log, what was our base? Good, 3. Our exponent this time was x, and what's left is 4.6. Okay? Okay, so sorry, the directions for this one sort of got caught here. Change each logarithmic statement to an equivalent statement involving an exponent. So here we're taking it from logarithmic form and changing it to exponential. So this would be if and only if what? So the base is 3. A logarithm is an exponent, so the negative 2 goes here, and what's left? Perfect, 1/9. What about this guy? Good, the base is 6. A logarithm is an exponent, so the x goes in the power, and it's equal to 2. And lastly, the base is e. Logarithm is an exponent, so the 5 is in the power, and what's left over is x. Perfect, and these were if and only if statements. I think my kitty's trying to help us. He's meowing up a storm. I'm not sure if you can hear him. Sorry about that. Okay, so here we go. Now, one thing to kind of get in your mind is instead of just tripping out about, this log business, if you just understand what it means. So what a logarithm literally means is, for part A, the power to which we raise 6 to get 1 over 216. So one way a person could do this is, couldn't you write this as log base 6? And what is 1 over 216? Isn't that 6 raised to the, perfect, to the negative 3 power? So the power to which I raise 6 to get 6 to the negative 3 is, awesome, negative 3. So I've evaluated that logarithmic expression. What about this guy? The power to which I raise 3 to get 81. You might have already known it. You could write it like this, right? Log base 3 of 3 to the 4th. So the power to which I raise 3 to get 3 to the 4th is 4. Good. All right, the power to which I raise e to get e to the 1. Notice that I know it looks weird, but you can write e as e to the 1, can't you? So the power to which I raise e to get e to the 1 is 1. Alrighty. So next up, we're looking at domain. So remember that the domain of a logarithmic function was all positive real numbers. So we basically want to take what's inside that log, and we want to say it has to be good, greater than 0. So this one, if you take away 7 from both sides, x has to be greater than -7, so the domain in interval notation will be good, -7 to infinity. Okay, so part B, this one's kind of a mean one. We've got x squared minus 16, so x squared minus 16 has to be greater than 0. Now remember, when you're doing a polynomial inequality, if you just do your related equation, f at x is x squared minus 16, and if you did the zeros, you'd have this. So 16 would be x squared, so plus or minus 4 would be your x. So that would divide up, you divide it up into a number line. You have -4 and 4. So minus infinity to -4 is that interval. -4 to 4 is here, and 4 to infinity is here. And we'll do test values. So f evaluated at negative, let's do maybe like -5, 0, and +5. So f evaluated at -5 for our test value is, what is it, -5 quantity squared minus 16, which is 25 minus 16, which is 9, I think, which is greater than 0, actually. And then f evaluated at 0 will be 0 squared minus 16, which is -16, which is less than 0. And f at 5 will be the same as f at -5. And so we'll get a positive. Now we wanted to take the positive results. So the domain for this one will be good, minus infinity to -4, union 4 to infinity. Okay, so far? Good. All right. Next up, -x has to be greater than 0. So if you multiply both sides by -1, then we'll get x is less than 0. We have to reverse the inequality. So the domain for this one will be good, minus infinity to 0. And we're all set. How's it going? We good? The better you learn this here in pre-calculus, the more easy calculus will go for you. A lot of times people in calculus have trouble because they've forgotten all their work with logarithms. So just make sure you keep up to date with logs. All right, so properties of the logarithmic function. F at x is log base a at x. So the domain is the set of positive real numbers, or 0 to infinity non-inclusive using interval notation. The range is the set of all real numbers, or minus infinity to infinity using interval notation. The x-intercept of the graph is 1. There is no y-intercept. The y-axis, which is also the line x equals 0, is a vertical asymptote of the graph. Okay, a logarithmic function is decreasing if the base falls between 0 and 1, and increasing rather if the base is greater than 1. The graph of f contains the points 1, 0, a, 1, and 1 over a, negative 1. And the graph of f is smooth and continuous with no corners or gaps. Okay, so let's go name that f inverse function. Remember way back, warm up 2. So the inverse graph that we did over here, this green guy, so remember f at x was equal to 2 to the x. Well, the inverse function, f inverse at x, is equal to log base 2 at x. All right? Okay. Coming back here. Okay, so this one, I had set it up where we'd be plotting points, but I think for graph B, we'll use transformations. So let's go ahead. I meant to rename this G of X here, and we're going to use, let's make this a little smaller. We're going to use transformations. Okay. So let's get this guy figured out first. So remember that, what does this expression mean? This expression means the power to which we raise 3 to get x. So whatever that becomes is what our function value is. So do our scale. Okay, so for x, since log base 3 at x is the power to which we raise 3 to get x, we want x to be powers of 3, or expressions which are powers of 3. So starting small, right? If I think about x being negative 2, so not negative 2. If I think of x being positive 1/9. So f at 1/9 is equal to the power to which we raise 3 to get 1/9, which is, good, negative 2. So we get the ordered pair 1/9, negative 2. And then let's do 1/3. So f at 1/3 is the power to which we raise 3 to get 1/3, which is, good, negative 1. And then f at 1 is the power to which we raise 3 to get 1, good, which is 0. So 1, 0. And then 3, the power to which we raise 3 to get 3 is, great, 1. And then we'll have 9. So f at 9 is the power to which we raise 3 to get 9, which is 2. Now, some people just don't see it like that. So what you could do, okay, is you could say y equals log base 3 at x, if and only if, and you could switch it to exponential form. So you would have 3 to the y is equal to x. So then you'd be plugging in values for y, and you would get your values for x. So whichever way, it works for you to graph it, I'm good with. Okay? So here we go. Let's plot these points. So at 1/9 we were down here at -2. At a third we were at -1. And then 1, 0, 3, 1. And then over here 9, 2. So see how you have this vertical asymptote here. And that's our graph. Okay? All right, so this guy, we have, it's going to be, let's talk about this graph here. This is log base 3 at x minus 4. So how are these two graphs related? Well, the graph of g is what? The graph of g is the graph of f shifted how? Good. Shifted 4 units to the right. So instead of having a vertical asymptote at x equals 0, we'll have a vertical asymptote at x equal to 4. So if we just do the same scale, we won't get all the ordered pairs, but I think we'll get a good enough feel for the shape. So we'll have a vertical asymptote 1, 2, 3, 4 here, and to the right of this is where our graph will start. So we'd have an ordered pair. Do this. We'll have an ordered pair about here, and then here, and here, here, and then instead of a point at, oh, actually this one needs to be moved over, sorry. So we'd be 2 over and then 1 up, and then this one would be like, the other one would be over here. But we have the idea about the shape. Okay? How are we doing? Are we doing okay? Awesome. All right. So moving right along, we'll increase the window again. If the base of a logarithmic function is e, and this is used a lot, then we have the natural logarithmic function. We often use this function in applications. So the symbol ln denotes the natural logarithmic function. This comes from the Latin phrase logarithmus naturalis. So here we go. Y is equal to natural log at x if and only if e to the y is equal to x. So basically, instead of writing this as y equals log base e at x, we write it as y equals natural log at x. So you have to remember there's a base of e. So let's take a look at how this one looks. Let's check out our graphing calculator. So, oops. Okay, so let's go ahead and graph, in the first one, we'll graph I guess we'll do the exponential. Do you want to? Yeah, we'll do the exponential in the first one. So we would have e to the x. And then in the second one, why don't we do the line y equals x to show how it reflects across that. And then in our third one, we'll do natural log at x. Oh, we'll have to zoom this differently. We'll just try zoom standard. All right, so actually let's push the window in a little bit. So the x minimum, we could just do -5 and 5. And then the y minimum, we'll just do, no, that was good. We'll keep it -10 to 10 on the y. Kind of messed up our, let's try zooming square, sorry. I was trying to get a nice picture of it for you. We'll probably just stick with this guy. All right, this works for me. Okay, so let's label these. So this here is our line, y equals x, the line that they reflect across. This guy here that's y equals e to the x. And this guy here is y equals natural log at x. And this was y equals x. Okay? All right, so if the base of a logarithmic function is the number 10, then we have the common logarithmic function. If the base of the logarithmic function is not indicated and you have an log, it's understood to be 10. So basically log base 10 at x, if you have y equals log base 10 at x, it's written as y equals log x. You would just need to know that the base is 10 if you see that one. So if you see ln at x, it's a base of, you got it, e. And if you see log at x, it is a base of 10. Okay, so y is equal to log at x, if and only if 10 to the y is equal to x. So in the next examples, let's go ahead and practice using our graphing calculator. There are some techniques that you need to learn about where to put parentheses so that you don't get the wrong answer from your calculator. So in part A, you go to the natural log key, and it's natural log at 5. Now be careful, you have to end this parentheses before you divide. Otherwise you'd be dividing by 8 within the log and you'd get a different answer. So this guy is approximately this. Right, so approximately, it said what, to 3 decimal places? Okay. So this is approximately 0.201. All right, so the next one, let's see how we would enter it in. Go ahead and pause the movie and try it on your own if you'd like. This one we have common log at 2/3, so 2 divided by 3. end parenthesis, and then divided by negative 0.2. So we get, I'll go ahead and copy this. So this one to 3 decimal places is approximately 0.880. All right, and then the third one has a bit going on. We need to be careful. We need to put parentheses around the numerator and the denominator. So parentheses, log, common log at 15, and then plus common log at 20, end parenthesis for the numerator, and then divided by parentheses natural log at 15 plus natural log at 20 and we get approximately 0.434. Oops. Okay. So here we go. Example 7, solve each equation and verify your results using a graphing calculator. So with these, what we're going to be doing at this point in time, we're going to learn about properties of logarithms in the next section. So for solving log equations in this section, you'll be doing a couple of different skills. Many of the times you will be rewriting them in exponential form and solving. So for example, part A, this is true if and only, so the base is 5, a logarithm is an good exponent, so 3 goes in the power, equals x. Well, 5 cubed is 125, so that's your solution. Okay, so then to check using the calculator, what we would need to do, because you haven't really learned the change of base formula. So for this one, I think on this one, you'll just have to take my word for it. Once we learn the change of base formula, then you can check these on the graphing calculator. But now you'd just be checking your exponential. So, okay, if we get one more complicated, I guess we can check it. Let's see this one. So, what we have going on is the base again is 3, or the base is 3. A logarithm is an exponent, so you'll have 3 squared equals what's inside, which was 3x minus 2. So we'll get 9 equals 3x minus 2. 11, adding 2 to both sides, is 3x, and dividing both sides by 3, we'll get 11 thirds is x. And so that is our solution, 11 thirds. Actually, yeah, we just need to, I'll teach you how to check things like this in the next lesson, most likely. Okay, so next up, natural log at e to the negative 2x is equal to 8. So if I switch this, it's a little tricky. If I switch this into exponential form, what is the base of the natural log? Good. The base is e, remember? So you'll get e. All right, so a logarithm is an exponent. So e is going to be raised to the eighth. And then you're going to get what's inside over here, which is e to the negative 2x. But notice we have e to the eighth equals e to the negative 2x. So we can use that skill where we equate the powers. So 8 is equal to negative 2x. Negative 4 is equal to x. And you're done. Okay. Next up, this is another sort of tricky one. What is the power to which we raise 6 to get 36? So I'm basically saying, what is this number? The power to which I raise 6 to get 36 is, you could think about it as the power to which I raise 6 to get 6 squared is, I'll let you think about it. Good. So this here, this part in the red, the power to which I raise 6 to get 6 squared is 2. So then 2 is equal to 5x plus 3. So then we have, if I take away 3 from both sides, I get negative 1 is 5x. And dividing by 5, I get negative 1/5 is x. Okay. Part E. So I have the common log. What is the base of the common log? Perfect. It's 10. So rewriting this in exponential form, we have, good, 10 to the fourth is equal to x squared. So if I go straight from there and square root both sides, I will get plus or minus 10 squared is equal to x. So plus or minus 100 is equal to x. And you have to take a look at that negative, but the negative will be okay because you're squaring the inside, right? You're squaring the inside. So on this one, we could actually check using the graphing calculator because we have the, actually the last two we could check using the graphing calculator because we have the common logs and the natural logs. So let's do that. So we had on one side we had log at x squared, and on the other side we had 4. And this one, remember, we have really big numbers. So this is kind of a cool graph. We're going to have to go, in order to figure out where they intersect, we're going to have to increase. Because remember, we got plus or minus 100 for x. So let's see. Let's go to maybe negative 150. To 150. And then let's do the scale on x as, I don't know, 10, I guess. And then the y minimum didn't look to be too low, so let's just do negative 2. See what we get. Graph. And there we have our intersections. We'll do one of them, and we can do both of them. So let's do a second calculate intersect. And first curve, second curve. Oh, I guess I'm not on there. Okay, first curve here, second curve here, So it found the left side. So see, we have it verified in here. So that's the negative side. And then the positive side will be, let's see if I can do it without going again. Now, let me do a second. Calculate, intersect. So we need to go closer to the other intersection point. That should be good. Here we have it, plus or minus 100. They both work. Okay? And then while we're at it, we might as well verify. Where was the one where we had the natural log? We can verify this one. So let's go here. I'm going to go to, we didn't have big numbers here. I'm going to go to Zoom Standard so that we can okay, so we will have y equals natural log at e raised to the negative 2 times x. And then the other side was 8. So if we graph, it's kind of trippy, right? Because it turns linear as we saw when we put it into the other format. So here, let's go to second calculate value. Oh no, actually second calculate intersect. And we verified it. When x is negative 4, y is 8. All right. Okay, so where are we at? So this is, let's use our graphing calculator to solve this one. We'll do it much in the way that we were doing it to verify, except we won't know the answer for sure. So if we go to y equals, I'll put in all the y equals and stuff for here. The first one, the left side is 4 times e raised to the x plus 1. And then the second one will be 5. So that's what we entered into the menu. And if we graph, see what we get. There's the exponential, and there's y is 5. So if we go to second calculate intersection, so it looks like we get, we'll have an approximate. Okay, so our intersection, if we, let's go to, I don't know, we'll go to 4 digits. So x is approximately negative 0.7769. Okay. All right. So a couple applications. I chose the ones that we had done in the last section, so that this time we're solving for a different portion of it. We, before, you know, we had the number of days, and we were figuring out the size of the wound, and now we'll be given the size um, given the current size of the wound, we want to find the number of days. So, and by the way, this, if you're, I keep forgetting people view these on YouTube without being in our class. If you're just viewing this, my video for the first time, you can go ahead and read over. This is kind of a cool problem about how the normal healing of wounds is modeled. So A0 is the original area of the wound, and A equals the area of the wound. So here we go. If healing is taking place, after how many days will the wound be 1/2 its original size? So the original size is what? Good, the original size is A0. So half the original size, we could let A equal 0.5 times A0. Isn't that half the original size? Good. So 0.5 times A0 equals A0e to the negative 0.35n. So the A0s divide out, and we get 0.5 equals e to the negative 0.35 times n. Now we're going to, since our unknown is in the power, what we're going to do is we're going to switch this into exponential form. So we want to switch to logarithmic form. And remember that log base e is natural log. So a logarithm is an exponent. So we'll have natural log because we have a base of e. The exponent is negative 0.35n. The only thing left is 0.5. Isolating the n, if we divide both sides by negative 0.35, we will get n is approximately, let's check it out. So natural log at 0.5, remember to end the parenthesis, divided by negative 0.35 is approximately 1.98 days. Okay? And then what about how long would we have to wait before the wound is 10% of its original size? So what would we let A equal? Good. We'd let A equal 10%, which is 0.1 of A0. So then we'd have the A0s again would divide out. And then, so we have 0.1 is e to the negative 0.35n. So now we change to logarithmic form. Since we have a base of e, it'll be the natural log. And again, we'll have a more definitive way. We'll be logging both sides of this after we learn more properties of logs. But changing to logarithmic form, natural log takes care of that base of e. A logarithm is an exponent, so we get negative 0.35 times n, and what's left is the 0.1. And then dividing both sides by negative 0.35, we will get n is approximately, So I'm just going to do, I'll clear this. Let me see if I can do second enter. So this will be 0.1 instead of 0.5. And we get approximately 6.58 days. Okay. So next up, again, this is the application I used in the last section. I believe it's similar. And we have to find some different things. So first we have this function that psychologists sometimes use, L at t equals a times quantity 1 minus e raised to the negative kt, to measure the amount L learned at time t. So the number a represents the amount that you need to learn, and the number k measures the rate of learning. So if we let a equal 200, so a student has 200 vocabulary words they have to learn. And we've been given a starting point. So we've been given that a is 200. We've also been given that L evaluated at a time of 5 minutes is equal to 20 from that one line. So what does that mean? That means that 20 is equal to 200 times 1 minus e to the negative k times 5. So n for t, whoops, that's too big. N for the t here, I put 5. And n for the a, this is fixed for this problem, we put 200. So we will have, if I divide both sides by 200, to isolate the exponential, we'll have, that's going to be 1/10, or 0.1 is equal to, those divide out, 1 minus e to the negative 5k. So if I'm going to go ahead and add the exponential to this side. So e to the negative 5k is equal to 1 minus 1/10 is 9/10. So we'll get 0.9. And switching to logarithmic form, we'll have natural log because we have a base of e. A logarithm is an exponent, so we'll get negative 5k, and what remains is 0.9. So going to our, calculator, we'll have just, we can clean this one up a little bit. So this is, we need, oh, actually, I'm ahead of myself. Hang on. If we divide both sides by negative 5, k is going to be approximately, I didn't mean to open this one and closing it. Okay. A is going to be k is going to be approximately, so we need to have it be divided by 5. And this changes to 9/10. So let's see, to 4 digits, 0.0211. 1. So our model, okay, will be L at t is equal to, we know what A is. A was 200 times 1 minus e to the negative 0.0211 times t. So that's what we'll use to answer the next question. So after 10 minutes, now we're going to plug in 10 for t, and we already know k, and we already had A, so we're going to be finding the number of words learned after 10 minutes. So L at 10 is equal to 200 times 1 minus E to the negative 0.0211 times 10. So wherever I saw a T, I put in a 10 for this problem. So this is going to be approximately, get our calculator out, go to the other side, and clear this one. So we have 200 times parenthesis 1 minus E raised to the negative 0.0211 times 10. Enter. So it would take approximately 38 minutes. After 10 minutes, you'll learn approximately 38 words. So approximately 38 words. Okay, and this is how I plugged it in to the calculator. Okay. All right, let's see what we're supposed to find out this one. Okay, so after 15 minutes, we're basically just evaluating L at 15 is going to be 200 times 1 minus E to the negative 0.0211 times 15. And we will get approximately, let's find out how many words. So instead of 10, we're going to do, clear this one, and do second enter. So instead of 10, we'll be putting in 15. So we get approximately 54 words learned. After 15 minutes. All right, so now a little bit different. How long will it take for the student to learn 180 words? So now we're looking for the number of minutes it'll take. So what do? Well, we'll set L at T equal to, good, 180. So we'll get 180 is equal to 200 times 1 minus E to the negative 0.0211 T. So again, in for L at T, we plugged in 180 words. So if we divide, sorry it's been a long day, guys. If we divide both sides by 200, it'll divide out on the right. We can simplify on the right. I think this is 9 over 10, so we'll get 0.99 tenths is equal to 1 minus E to the negative 0.0211 T. Now we need to get the exponential isolated before we can solve for T. So again, if I add the exponential to both sides, I get E raised to the negative 0.0211 T is equal to 1 minus 0.9, which will be 0.1. And we'll have switching this into log form, since we have an e as the base, it'll be natural log. A logarithm is an exponent, so we'll have negative 0.0211 times t, and then what's left, 0.1. So dividing both sides by negative 0.0211, we'll have t is approximately okay, so what did we have? We had natural log of 0.1 and close the parenthesis before you divide. And we're dividing by negative 0.0211 equals, it looks like it'll take about 109. I think that's right. Yeah, about 109.13 minutes, 0.13 minutes. To learn 180 words. So if you're thinking about this for like a Spanish class or French class, depending on what you're taking, you need to put some time in to learn those words, right? Okay, so you know what? I think that wraps it up for today. Have a wonderful evening, and I'll talk to you later. Bye.